have the floor.
Yeah, hello everybody. Many thanks, Professor Alves. Thank you, Luis, for inviting me here. Actually, this talk was intended already last year. Unfortunately, I got sick, and so we had to postpone it for a year. I'm very happy to be here, and I'm very grateful also to you coming here on such a nice sunny afternoon to this windowless hall just to listen to my talk. Thank you very much. So the talk is about kinetic effects in low temperature plasmas, as was already mentioned in the introduction. And why is this not working? It's not working.
Is this Yes, so unfortunately it is not.
That's a good start.
Yes.
Well, maybe in the meantime I can say a few words. You will see soon the contents of my talk. But write a disclaimer, of course. There are so many kinetic effects that I will not talk about all of them, but a selected example, as you might have expected already. And secondly, another disclaimer is that the term kinetics is not so clearly defined. Often kinetics is understood the interaction of electrons with excited states of atoms or molecules, and this excitation is then called a kinetic interaction. This is not the topic today. So here we...
Unfortunately, I think you need to come here to switch the slide. This is probably connected with the Zoom, so...
Yeah, okay.
Ah, it is worse than this, so... Yeah, so it is the mouse. Should be the mouse.
So how do I do it?
Just click the mouse.
No, it should work. No, it should work. Can you try now the keyboard?
No, it works. Yeah,
No,
indeed.
works, yeah.
Well, first of all, let me show you where I'm coming from. I'm coming from the Ruhr University Bochum, which is in Germany and in the state of North Rhine-Westphalia, which is here not so far from the Dutch border, but it's in the heart of the so-called Ruhr area, which has a reputation of being completely dark because it was famous for coal mining. But as you can see, it's a very green area nowadays. Coal mining has vanished, and it's a really beautiful place, and you might visit it. The Ruhr University has really basically all kinds of sciences on its campus, so it has 21 faculties, around 40,000 students. I think it's about more 39,000 at present, about 3,000 scientists, and then about 400 full professors. So it's one of the largest universities in Germany. So the selected examples I will talk about are the Fokker-Planck Langevin operator, as already introduced by Professor Alves, for electron field interaction. Also in the introduction was the inductively coupled array discharge. The acronym is INCA. And finally, briefly also on some kinetic effects in ion transport and how they relate to a fluid description. But first of all, let me give you some brief introduction and then talk a little bit about the Boltzmann equation, because I was told not everybody is so familiar with plasmas, and I would like to help those to get a little start here. So obviously, plasmas are many particle systems. And these low temperature plasmas we are talking about, low temperature means electron temperatures of a couple of electron volts. They typically consist of three ensembles of particles, namely electrons, ions, and neutrals, that might be atoms or molecules. Well, you can further distinguish if you look for dissociation and so on, but that is a secondary aspect today. So these low temperature plasmas are usually not in thermal equilibrium, and that's where the fun comes actually in. So you have these three ensembles of particles which are not in equilibrium with each other. And even within an ensemble, the charged particles are not in equilibrium. The reason for this in short terms is that we have a low partial ionization degree, and this is combined with a very finite confinement time, and this does simply not allow for a sufficient number of Coulomb's collisions which would be needed in order to reach equilibrium. So the velocity distribution functions are mostly not Maxwellian, although for demonstrations and often also in calculations people love to use Maxwellian distributions. I will even do the same thing later on, but generally they are not Maxwellian, and this is an important aspect. So we have to determine the distribution function, and the standard way is by using the Boltzmann equation. So here today I will introduce an alternative approach which is based on the Fokker-Planck-Langevin equation. Usually the Fokker-Planck equation in plasma physics is thought to describe collisions, especially Coulomb collisions, but here I will show that this is a very nice equation also to describe the interaction with external fields. So that means the electron heating. And electron heating means that this is generally a superposition of local ohmic heating and non-local heating, which often is called stochastic heating. And we will see that nevertheless it has a lot to do with collisions. And both effects can be combined in one single operator. Non-local heating is related to the thermal motion of the electrons, so it's a hot plasma effect. And there are resonances in velocity space, so namely when the particle velocity equals the phase velocity of certain waves. So even if you don't launch a wave, structures in the plasma effectively can be understood in the terms of waves after Fourier transformation. And this insight allows then for the design of a new discharge. This was the Inca discharge, where we have a new energy coupling concept with tailored electric field structures. And finally, non-local kinetic effects exist also in this case, ambipolar ion transport. And understanding these kinetic effects finally allows for a closure of the momentum equations and calculation of the ion temperature, which is not a trivial thing and couldn't be done so far. So this is the famous Boltzmann equation, and this acronym here on the right-hand side is, of course, where lots of the difficulties originate from. This is the collision operator. That means this operator describes the interaction of the particles, namely in the electrons or ions, with atoms in the system. So it's easy to write down. The operators might need a little more work, and the knowledge of a related cross-section might need even more work. And I know that especially here in Lisbon, you are very much working on this. But while it's easy to write down, it's incredibly difficult usually to solve. One way is or a standard way is the ansatz is that we separate the distribution function into an isotropic part, which depends only, especially for the electrons, not for the ions, but for the electrons, into an isotropic part, and which is also stationary and time dependent. Typically harmonic part, which is non-isotropic. This non-isotropic part is related to the current, while the isotropic part is related to all these collisions, so it's related to the excitation, to the power balance, to the ionization, and so on. And after we do a bit of linearization with this ansatz, we finally get a nice balance between some heating operator and some dissipation operator. As you can easily imagine, the energy which goes in has to be dissipated in order to have a stationary situation. So I put already here an average over the spatial coordinate, and that relates to the situation I want to describe in today's talk. Because if we go to sufficiently low pressure, that means sufficiently low collisionality, the energy relaxation length becomes larger than the system size. In this case, there's only one non-local distribution function, which is a wonderful thing. So this distribution function, as I wrote down here, is just a function of the total energy. That means the sum of the kinetic energy of the electrons and the potential energy in the plasma potential. Here you see an experimental evidence for this. So this is in a cylindrical plasma, and measurements of electron velocity distributions are made at different radii and then shifted by the local plasma potential. So shifted by the local plasma potential, and you see that then these are indications of a different radii here, but you see that all the distribution functions fall on top of each other. That's the case at sufficiently low pressure. If we go to higher pressures, well, it's still maybe good. And if you go further to higher pressures, that fails. And if you go to very high pressures, then you need a lot of local distribution functions. But we are talking about a situation where this applies here. Keep that in mind. So there's only one distribution functions. So nevertheless, let's step back and talk for a minute about local ohmic heating in order to understand what the heating operator actually is doing. So, and that is local ohmic heating. So imagine a homogeneous oscillatory field. There's nothing about this non-locality, and where the heating operator has this form. So this was the left-hand side of this balance I introduced before. And well, there are some derivatives, and there is this, what I call GO. This is the coupling function, and for the local ohmic heating, this coupling function here has a very simple form and depends only on the elastic collision frequency divided by the frequency of the oscillatory field. So this is for an oscillatory field here. And we will later see that this general form of the operator we will find also in general. The only difference will be that this coupling function changes. And this is good, because this is how we can easily collaborate, because you have a Loki code here, and the only thing which has to be exchanged in order to go from local heating to a mixture of local and non-local heating is to plug in here the appropriate coupling function, which then, of course, is more complicated. But still, this looks very abstract. But if you put in a Maxwell distribution, assume the collision frequency is not velocity dependent. In reality, it is. But for the visualization, we can assume that. Here, I assumed that the ratio of the collision frequency to the oscillatory frequency of the field is simply 1. You see, this is the form of the operator for not the velocity distribution function, but for the energy distribution function, because we have the isotropic velocity distribution function, depends only on the absolute value of the velocity, and then we can as well write it as a function of energy, and that's the energy distribution function here. And you see the operator is doing just what you might expect without any mathematics. it takes cold particles, particles with low kinetic energy, and moves it to the high energy part. And the division line here is actually at the mean thermal energy. This is exactly the division line in this case. And we will find that later on, this is actually quite generally the division line. So with low energy electrons, that's why it's negative. They are taken out of a distribution and then put into the distribution here at higher energies. Of course, in total, when, it's particle conserving. We don't lose electrons. We just take electrons from the low energy and put them to the high energy. So with the Boltzmann equation, we can, of course, address also with the non-local case, and that is the answer. Well, maybe someone got a heart attack. This doesn't look very nice. It looks incredibly complicated, and there are here averages about space and time and solid angle even, and this is an incredibly complicated expression. And then it's a little bit like this famous quote in quantum mechanics, shut up and calculate. So where all the problems are purely mathematical, but where's the physics? So the Boltzmann equation is an incredibly nice equation if you just want a result. It's straightforward, and well, that was also straightforward. It's straightforward. What is happening here? Yeah, so, no, one more? Yeah, now I got it. So it's straightforward for the calculation, but it's very hard to interpret later on what the physics, what the underlying physics is. You must really bring it with extra effort. So, and then the question is, of course, is there a more physical approach leading to the same result? And there is, and that was the topic of the collaboration between Professor Alves and me. And that paper, which is almost a kind of book with almost 100 pages. I'm not sure anybody is really reading it. It's well downloaded, but I'm not so sure about anybody reading it. It's good to have it in the shelf, just in case. And it's about describing local and non-local electron heating by the Fokker-Planck equation. So actually, it's a Fokker-Planck Langevin equation combination, and it's about combined. So it's about the formulation of the relevant equation. It's about combined local and non-local electron heating. It's also about self-consistent electric field structure by a generalized dispersion integral. And most importantly for our ongoing collaboration is a global kinetic plasma model, which can be used in a local Boltzmann solver in Loki, and that is what we will be working on over the next couple of weeks and here, and then, of course, also when I've returned back to Bochum. So the Fokker-Planck equation is known for more than a century. And it has, it looks like this. So it has two nice terms. One is a so-called drift term, and one is a diffusion term. And it was originally formulated in order to describe what was the hot topic at that time. Last not least, at that time, Einstein understood diffusion in terms of this random motion. This is the diffusion term, this is the drift term, and you have here the random walker trying to get home with some probability. Except that with the random walker is, of course, walking in configuration space, but here you can, here for us it's most important in velocity space, but there's also application in energy space. And generally in the stochastic literature, you can apply it to almost any kind of space. But it has always these two terms. That was nice, but it was not correct. That is the equation, if you look into the literature, you find. Something which is usually not said in the stochastic literature, because it seems that the stochastic physicists take it so much for granted that there's no point discussing about it, is that the collision frequency, which you see here, is a constant. Well, you know very well that in plasmas this is not the case. This depends on the velocity. And if you use this form of the equation, as I will show in a minute, everything goes wrong. You really have to go back to the master equation, perform again consistently the Kramers-Moyal expansion, and then you will find a slightly different form, which is down here. And the only thing which happens is that we move, you see this is the second derivative here, that we move one of the derivative operators from here to here. It seems such an innocent thing, but it makes a huge difference. Another nice point, so that I said this is a wonderful equation, yes, but you see we have velocity changes here. These velocity changes are the velocity changes in a collisional interaction. Well, what are these velocity changes? That does the Fokker-Planck equation not tell you. So you are supposed to know it from somewhere else. A colleague tells you, or on the floor, suddenly, well, this morning I had a dream and that is the case or whatever. No, it's the Langevin equation. The Langevin equation is an awful equation to calculate anything except that you get this velocity changes. So you cannot really solve analytically the Langevin equation, but it gives you the coefficients we want to know. That's the good thing about the Langevin equation. But there's another point. It looks completely different than what we have in a plasma, because in a Langevin equation, it's basically an equation of motion, the Newton's equation of motion, with a friction term here, and some stochastic force. This is not what we want to describe, because in our plasmas we have a defined force. We have a field which is maybe periodic, but it's not stochastic. Well, but we can look, and we have to look, on a coarse timescale. And a coarse timescale means that we do not resolve these individual acceleration in the field, collision, acceleration in the field, collision, that we do not resolve this. In fact, also in the Boltzmann equation, the distribution function, which is a continuous function, never resolves these kind of things. It's a kind of average over a reasonable long or short time scale and also volume. So if we look on such a coarse time scale, if we have some acceleration in a certain period of time, which can vary from collision to collision, so it's a mean free flight time where the particle is accelerated. So, and depends also on the phase, if you have an oscillating field. So the velocity change over this free flight time is a random number. Then comes the scattering. The scattering is purely elastic and just puts the velocity vector, or gives the velocity vector a different direction. You can describe it by a rotation matrix, a random rotation matrix. But if we don't resolve this, it becomes a stochastic force. The stochastic force simply means we have a force where the strength is varying and the direction is varying. This is exactly if we don't resolve that. So we actually get the Langevin equation, And then we get a concept, a very simple concept for getting our velocity changes, because what we have to do is just integrate the equation of motion for our particles over a certain time. This is a certain free flight time. This free flight time is, of course, a stochastic parameter. And there might be other stochastic parameters, like the initial position of a particle or the initial time of a particle and so on. And then here in our Fokker-Planck equation, we have to average over these probability functions. So you see, that is something you don't have in the Boltzmann equation at all. Here we have to introduce probability functions. So all these probability functions are independent so that we can write them as a product. And of course, the underlying assumption of the Fokker-Planck equation, I didn't say that, I think, is that these are all Markov processes, so we have no back memory. That is also important, of course, to mention. So that is then the very simple concept how we describe our Fokker-Planck heating operator. I put these acronyms here, Fokker-Planck heating operator, it should be. So another thing is, in formulating it in this way, you have to state explicitly something which is incredibly important in understanding the physics. So a particle might gain energy in the field at some point as is accelerated. But then at another time, at another position, it might be scattered. And only this scattering actually introduces irreversibility. That is heating. And that means non-local. But this term in our community, unfortunately, energy gain and heating is completely confused. And that's not the same thing. The energy gain is what is in the field, and combined with the scattering, which introduces the irreversibility, it becomes heating. So ohmic means local. That means this is basically at the same place. Same place means the distance is short compared to any gradient length of the electric field. That is when it's local. And that is an important thing. You must state that here explicitly. You see also this is now a derivative only in one dimension. That includes already, because generally, because that was written before as an Einstein notation, so there were the indices, that this has all the velocity components, where only the diagonal modes contribute, and but all the free velocity components do the same thing because we have this random scattering. And then finally we can reduce it just to one direction. So there's a lot of physics already on this, up to this part, where we have just formulated our equation, which we would not get from the Boltzmann equation. So then I told you we had to modify it. So we can make a very simple test. We take an ergodic Monte Carlo test. Ergodic means that if we have it's the same thing if we have a large number of particles or we have a single particle and watch this single particle for a long time. So if you are at home and we watch you for a long time, eventually you will reach all the corners in your home with some probability. Maybe some corners more frequent, like the fridge, and other corners like the cupboard with a broom. Not so often, but that is the idea about the ergodic Monte Carlo thing. So, and here also the situation is very simple. We have only elastic collisions, which are allowed here to have a small energy transfer, which is really small due to the mass ratio between the electrons and the neutrals. So we keep everything simple so that we can trace it and actually analytically calculate it. And if we have a constant collision frequency, of course, it doesn't matter. Everything agrees, the analytical solution, the original form of a Fokker-Planck, this modified form of a Fokker-Planck, everything is the same, and we get this distribution function. However, if we go to the case of constant mean free path, then this is the analytical solution. This is the modified case here of Fokker-Planck equation, and that is the original form. And that is completely wrong, as you see. So a little wrong, it's completely wrong. It's a disaster. And if we can still understand this if in the Monte Carlo we assign a wrong statistical weight. Because with a constant mean free path, the statistical weight is related to the mean flight time. But so every event, free flight collision, has its own statistical weight, depending on the free flight time. But if we just assign the same statistical weight, which is of course wrong, then indeed we get this wrong solution. So you see what is happening here. So then the Fokker-Planck heating operator looks very much like the ohmic heating operator, except that we have here a different coupling function, and that is the main aim in the calculation. The special case we treat here is a transversal electromagnetic wave entering the plasma, which is an ICP or could even be a microwave. And that has, of course, to do with the electric field structure. And firstly, we assume a simple exponential decay, so the field structure is given. And secondly, the field structure is calculated self-consistently by solving, in addition, the Helmholtz equation. So an essential step now is that we integrate the equation of motion by using Fourier transform. That is a very essential step. And you see already here that we get this kind of kinetic resonances down here. And these kinetic resonances are in velocity space. That means when you see k times v, if it equals omega, we have a resonance, similar as in Landau damping. Then we have a very large contribution. So particle velocity equals the phase velocity of a wave that gives resonances. Processing further here, we find a form of the coupling function I mentioned, which looks extremely nice to my opinion, because we can separate it into the electric field, or exactly the absolute square of a Fourier transform of the electric field, which serves like a kind of probability function. So you might, this resembles very much what you would have in quantum mechanics if that would be psi. Yeah, when it would be psi square, and you would have such a kind of form. And this is the response function of the system, with small gamma. This small gamma depends on collision frequency over the oscillation frequency, like we had it in the ohmic case. And in general, for the For these resonances, we need the wave number times the velocity over omega. This is exactly, you see here, the velocity over the phase velocity, which is the second parameter. So we have exactly these two parameters, but this is a general response function of the system, and believe it or not, you can calculate it analytically. You get an analytical expression. The expression, well, it looks complicated. You might expect that. But we can easily visualize it. This visualization is here. So on this axis is the collisionality. On that axis here is this ratio of velocity to the phase velocity. And if we are somewhere here, then everything is ohmic. We have a high collisionality, and this function is pretty flat. Whatever this ratio here is, doesn't matter. But if we go to the collisional regime, so it's here it would be completely collisionless, then we see a strange thing. There is this gap. There's nothing happening here until 1. And then it comes up, and but there is this gap. This gap is not introduced by us. It comes directly out of the calculation, and it's very, very physical. Because if velocity is too large, we need the resonance. We can always project it, because it's the absolute velocity here. We can always find a projection of a velocity so that the projection on the propagation of a wave matches the phase velocity. That is possible. But once it becomes too small, you can rotate it as much as you want, you will never reach the phase velocity. And that is clearly here if the ratio is below 1. Therefore, we have this gap. And this physical insight also you hardly get from the Boltzmann equation. And here it comes out in a very, very natural way. Further, you see that this has to be larger than 1. That means that the kz, because we assume that the electric field varies in z direction, that is the reason why the index is at z here, times the velocity must be larger than omega 0, so that we can make the projection. And if the hand-waving argument is that k is something like 2 pi over the decay length of the electric field, then you see that the velocity should be larger than this decay length, which is basically the gradient length of the field over the time the field is changing. So in other words, a particle which goes into this inhomogeneous oscillating field must go in and get out before the field has changed its sign. If it stays in there for too long, it just makes the quiver motion, and that's boring. It doesn't gain any energy. So the trick is get in, get out before we catch you. Yeah, so that is the idea. And if we look here at the distribution function, that doesn't know anything about the distribution function, but we can introduce the thermal velocity here. Then the thermal velocity should be larger than an effective velocity, which is this gradient length times the RF frequency. That's a simple argument you find here. Okay, so again, we want to visualize things. And for this, we assume again a Maxwell distribution and an exponential decay to keep it simple. And I have plotted here 3 situations. One is a high, well, moderate, relatively high collisionality, so nu over omega is 1. Then the average, where it's 1/2, and the low, where it's 0.1. So I said that the thermal motion is important, and in each of these graphs we have a lot of curves, sorry, and these curves relate to a temperature parameter, which is simply the temperature, basically the thermal velocity squared over this velocity as omega I introduced before, this effective velocity. So at high collisionality, no matter what this thermal parameter is, we get all the same curves, and this is exactly the same thing as we had for the local ohmic heating. That is a situation which is basically only ohmic heating, everything is local. Well, if we go to 1/2, you see there is a difference. And if we go well below 1, which is here 0.1, that makes a big difference. So if we if this parameter here is too low, there is not much heating. So the particles must move fast enough, as I said, to get in and out thermally. If the particle gets faster and faster and faster, this is saturating, and then we get back actually to the same form and even the same amplitude as in the ohmic case. You see here this curve, the final curve here, which is already for this parameter 32, is kind of saturation, and that is the same curve here as in the local case. So in this case, really the non-local heating can be as efficient as the local ohmic heating. It has the same heating operator in this case. So, but this was for an exponential field. If we want to know the field, then of course we have to calculate the field structure, which results from the fact that we dissipate in the plasma. So the field and the particles exchange energy, and that defines then the field structure. Fortunately, as you have seen, the only thing we need is the absolute square of the Fourier transform of the electric field. And this is good news, because we can solve the Helmholtz equation directly in Fourier space, and we never have to go back to configuration space, because we only need this absolute square of the Fourier transform of the electric field. And by doing this, we can identify a so-called, or what I called a dispersion integral, which is directly related to the complex conductivity. The sigma here is the complex conductivity. So there's a 1-to-1 relation with some factors. And that is a very nice thing, because we can exactly solve this. So what remains finally is just a long integral analytical expression. Because it's so long, I didn't put it here, but it's an analytical expression. There's one essential step in this, which we applied also to Landau damping and other things, because usually there are two assumptions made. If you think back of your basic plasma physics courses in Landau damping, you assume A, a Maxwell distribution, and B, either you assume there are no collisions, or if there are collisions, the collision frequency is again assumed constant. Neither is true here in our case. So the way out of it is, because everything depends only on the absolute velocity, we can do the angular integration. And that allows us to find explicit expressions. And then we can identify this absolute field here, and this is just the real and the imaginary part of this dispersion integral. So having all solved this, then we get the balance. Well, I added here one more term to the balance. So the interaction with the field, which is the heating operator, the dissipation operator, which is the usual dissipation operator for collisions in a plasma, which is well established in Loci. And there's a new term which also accounts for surface losses, because the usual Boltzmann solver is a local Boltzmann solver. It does not know about any surfaces or any structures. It's a local thing. So then you never think about surfaces. But if we go to the low pressure, I said we have large mean free paths, then of course particles simply escape to the wall. And then we have to take into account this. We lose particles, which has to be balanced by ionization, but we lose also, when we lose electrons, we carry also away energy. And that has to be accounted for. So that is the situation we address here. And well, we had already some test runs, and well, it was depending on the status of the implementation, say it was something between seconds and minutes of calculation.
More towards the second.
Maybe more of a minutes, but by the ideas we have, there might be some more minutes, but still it's minutes. So the input, you put in the type of gas, the neutral pressure, or the neutral gas density, the geometry data, the volume, the frequency of the field, VRF power, and what you get out is a global isotropic electron velocity distribution function, all the moments related to this, the electron density, the electric field strength and structure, and the plasma potential, because that is related to this. So these are some assumptions which are made there. One particular feature is that you have three initially not known parameters. One is electron density averaged over the volume, the ratio to the electron density at the edge of the plasma, then the sheaf potential, and the electric field or the current density in the coil, which induces or launches the electric field. And you can self-consistently determine this parameter, but you need in addition an ion transport model to calculate the ionization rate, which is related to the ion transport. What we need an ion transport model is not just an excuse. Last not least, we are describing a plasma, and a plasma is consisting of electrons and ions. Would be scary if we could just deal with the electrons. The electrons can do a lot of things, but we cannot do it without the ions. So, and because they are related. And therefore we need this ion transport model. So let me, and that can be different things. It can be a simple analytic model, it can be a numerical model. Well, it depends on what you want to do. Having learned that we need this wave structure, I want to introduce to you an inductively coupled array, which is something which is my personal answer to solid state physics. Because I always envied the solid state physicists. Are there any here? Because they can make structures. The solid state physics, they can make structures and then they have a new effect with these new structures. In plasma physics, the plasma makes some structure and then we can study them for years and eventually use them for something. But it's not us making it, it's the plasma. Here I wanted to make structure. And the way we can do this is by introducing an array of vortex fields in a plane. And that can be scaled up and introduces designed resonances in velocity space. So you see that is a part of this structure. You see all these coils. And these coils eventually then introduce some vortex fields. And depending on the phase between the coils, which is the simplest case where all coils are in phase, you get a primitive cell after which it reproduces. If every second coil is 180 degrees out of phase, which we call the para-array, this arrangement we call the auto-array. But in the para-array, the primitive cell is twice as large. So, but today I want to just stay with this auto-array where everything is in phase. Why does it work? Well, imagine an electron is accelerated in this direction. So it will see a wobbling field, but this wobbling field has always a positive projection for the acceleration. So electron will always be accelerated this way. There is some left and right acceleration, but they average out. Well, after half an RF period, it would reverse and there would be no gain. But if, well, not sure why it's not working. No, this is the PDF. Yeah, so if it, this is a PDF, it's not the PowerPoint. If an electron moves thermally perpendicular in this direction, then it gets here in half an RF period, and then again it's further accelerated because the field has just changed in a way that can be further accelerated. So kinetically, we get these kind of resonances in velocity space. So we have velocity in x and y direction here. And if we make a Monte Carlo simulation, we see exactly these resonances. You can also see them if we take the basic spatial Fourier component of these vortex fields, which look like this. But they can be re-expressed just as the sum of 8 waves. I call them pseudo waves because there's no dispersion relation. So we see we have this wave structure, but there's no dispersion relation. That's an essential point, because if we would have a dispersion relation, we would be, again, depending on what the plasma is doing. But because there is no dispersion relation, we are the master, and we define what's going on here. And that is a simple concept for a stochastic model. So a particle here comes basically from infinity or from inside the plasma, is reaching the surface where we have these vortex fields, and you see all these kinks which look like collisions, but there are no collisions. This is just due to the interaction with the field. In the calculation, we can identify 2 parameters. One is a temperature parameter, and one is what I call the locality parameter. So in our case, everything is non-local in the plane, but you have locality either in the vertical direction or in the perpendicular direction, or a non-locality. And that's exactly the opposite to what happens in a standard ICP discharge, inductively coupled plasma, which we discussed before. Just the opposite thing. Here you see this temperature dependence, and once the thermal velocity is large enough, there is very little variation with temperature. We almost have the same. This G is related to the power coupled to the plasma, which is a kind of power coupling function. You see it's varying because with large thermal velocity, the particles simply don't stay long enough in the heating zone. But otherwise, this change is so moderate that we can actually operate it over a really large range. That's what we built. So basically, it's a compromise between me and our technician. So my calculation were for an infinite array, and our technician was of the opinion one coil is enough, and that is the compromise here. And you see where the name Inca comes from an inductively coupled array, so there's the Inca. So the thing has a size of roughly 40 times 40 times 13 centimeter, 36 coils, and pressure we typically operated in between 0.1 and 10 Pascal. So this is the setup. There's also an issue with the wiring, which allows us to scale it up without changing the impedance, but I don't want to go into detail. Here the most important thing is that the transition initially, if you are at very low power, the power coupling is, as always, is capacitive, but the transition power here to this inductive or stochastic mode is extremely low. So if you calculate that power per area, it's about at 0.1 watt per square centimeter of that order, which is really very, very, very low. Tells you that the discharge is very efficient. It also scales, the electron density scales linearly with the dissipated power, which is to expected. Linearly also with the pressure over really a large range. And an amazing feature is once we go to the stochastic mode, the distribution function Maxwellized. You see if we are at higher pressures, we have this depleted tail, which is due to the inelastic collisions with the neutrals. But at once we go into the stochastic mode, that means that the electron can travel more than one cell size so that it can take advantage of these designed resonances. Then it becomes Maxwellian. And it's doing this in any gas. For example here for argon and O2, but it's for any gas, it's the same thing. So, and you see also that it works in basically any gases in a similar way, even in SF6. So whatever you put in there, you switch it on and be happy. So, 3 minutes, yeah. That's a challenge, but I will give my best. The last point I want to address briefly are kinetic effects for ions. I already said we need an ion transport model. And sometimes our community is good at putting things under a carpet and declaring things are okay. And on a kinetic level, things are okay because charge exchange collisions are perfectly well described for long by the Wannier collision operator, and which you can combine with the Boltzmann equation. So charge exchange collisions are not important so much in the center of the plasma, but once we get a little more to the wall, that means that the ion energy has increased to more than about a tenth of an eV when charge exchange collisions. This is a cross-section here. This is a particular case, I think, of argon, but it's more or less the same for other gases. When charge exchange collisions, symmetric charge exchange collisions, dominate. So this is a complicated operator, but it has a lot of merits. We would like for ions not to do actually the Boltzmann equation, solve the Boltzmann equation, but use the fluid equations, because we are not so much interested in the distribution functions. But there's a trick you need. You need a closure. The fluid equations follow by closing the momentum equations with some ad hoc argument, typically at the level of the energy balance equation. And that ad hoc argument cannot be derived. It can just, well, if you have the argument and it works, then it's good. But for charge exchange collisions, there have never been developed such an argument. Nevertheless, people were using even the momentum balance equation And ironically, the equation it was good, but the arguments made for using these equations were completely wrong. So that is a funny situation. And so if we look at the moment equations, then we can realize that we can, on all levels of the moment equations, we can write them down in the same form. And this same form, you see, it's a very simple first order differential equation. And this is a backward average. Backward average means that the distribution function basically at this point, or anything which happens at this point, is not only determined by what happened here, but also what happened spatially before, because ions are flowing from here to here. And the weighted average is, this weighted average is this exponential with 1 over lambda, which is simply the probability of a particle which started here to get here at the point where we want to know what happens. So otherwise the equations are not useful. I'm almost done. Please say one more slide. If we write down now the energy balance equation, we can identify, and we can split them, and we can identify the same form of backward averaged equation with an unknown function xi here. And for the ion temperature, which is an effective value with the thermal velocity averaged, and that wouldn't help because we don't know this function. But fortunately, we can solve it for a homogeneous field, and where this function is exactly 0. In general, this function depends on the higher moments. So now the closer hypothesis is that this function psi is negligible also in the general case. Then we have an equation, a backward average equation for both the temperature and the skewness with some general homogeneous heating term and a coupling term. So this term here couples the temperature to the skewness, and here the temperature couples to the temperature couples to the skewness, and the skewness to the temperature. Then we find the momentum balance equation, and that has exactly the form people has used for long, but for very, very different reasons. Also, it contains the ion temperature, which has not been known so far. And we can calculate this for various cases. And one is for a constant electron temperature. The other is a constant ion sound speed, which means basically the sum of electron and ion temperature are constant, which is a low plasma density case. The other is the high plasma density case. And these solutions are absolutely parameter free. So they are scaled only by the electron temperature, or more precisely, the temperature in the plasma. The trick is also that we make a transformation from the spatial coordinate to the flow velocity, because we have monotony here. Then we don't need any information on the size of the plasma either, because the velocity is clearly 0 in the center, and the bulk ends where the ions reach the sound speed. So this is the solution here for the temperature in case of constant ion sound speed. You see also that the correction by the skewness is very small for the ion temperature. The solid line is including the skewness. The dashed line is without the skewness. There's not so much difference. And you see that the skewness itself is making this sign change here. And the sign change can be understood really from the distribution function. So the distribution function in the center is half Gaussian, where the skewness is, which describes the asymmetry of the distribution function, where the skewness is positive, while at the edge, where we have the sound speed, we have this long tail due to the charge exchange collisions, and then clearly the skewness is negative as it should be. Compared to experiments, there's no fitting. This is really ab initio comparison. And you see for the ion temperature, the comparison is pretty good. It's still quite reasonable for the skewness. Of course, the error for the skewness is expected to be larger than for the temperature. But we can, for the first time, really calculate generally the ion temperature here. Well, then I come to the conclusions. Thank you for your patience. Thank you for your patience. I might not go through it, but just the last points. I think the kinetic effects in plasmas is really an old topic, and so you would think that there's not much juice in it anymore. But it's amazing what you can find if you just look. And so keep on looking. That is my message. And I have to thank, of course, all the collaborators here. And yeah, well, that's a supplement, sorry. That is Philip R., who was a PhD student working on Inca, Christian Ludwig-Stetzka and Eva, too, Zanko Zankov, too, and there was a lot of discussion with him, Dirk Lugenhölscher, who is involved in anything experimental in our group. Last not least, and most importantly here, of course, Luis Alves. Christo Tanev was also involved in the Monte Carlo simulation for Inca. And Wolfgang Paul is an old friend. He's a professor in Halle for stochastic physics, with whom I discussed a lot of the stochastic things. So thank you very much for your patience with slightly, more than slightly over-talking and ruin your afternoon. And thank you again.